Yeah, eventually. I'll begin though. Dear Father, we thank you for this day. I thank you for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. So yeah, if somebody wants to do the camera, you're welcome to sit there and move it around for me. I wouldn't mind. I just thought I should get started. Thanks, Joseph. So we are starting our work on partial differential equations. All right. So let's talk about that. A PDE, or partial differential equation, is a differential equation where you have more than one independent variable. All right? So what are some examples of partial differential equations? Well, here's a couple of examples. First of all, you could say, look at the, let's see here, I always forget the symbols in your book. So we're in chapter 10 here, and basically we'll be solving, let's see here, partial u, partial t, and in the notation of your book he puts a beta here, partial squared u, partial x squared. So this is the so-called heat equation. Here, u is a function of, x and t. This is the temperature. The temperature at position x at time t. Right? And so a typical thing we think about is like some kind of like rod where, you're looking at the rod that goes from, say, x equals to 0 to x equals to L, subject to various boundary conditions. Like maybe you've got both ends of the rod in like an ice bath, so they're fixed at, say, 0 degrees or something like that. Right? So we'll solve the heat equation subject to various boundary conditions is one of the problems we're going to solve here. This is the heat equation. Now beta is just a constant, which describes the particular thermal conductivity of the problem. This is an example of a diffusion equation where we're thinking about, heat diffusion, the diffusion of heat through the rod. And at the moment, that's just the heat equation in one dimension, right? If you wanted to talk about the heat equation in 2 dimensions, what would this look like? Partial u, partial t is something like beta times partial squared u, partial x squared, plus partial squared u, partial y squared. That would be the heat equation in 2 dimensions, in 2 Cartesian variables. Or if you wanted to be sort of a little bit more sophisticated, you say it's beta times the Laplacian of u, right? Where this is the Laplacian of u. So that, in 3 dimensions, it would be the partial u squared, partial x squared, plus partial u squared, partial y squared, plus partial u squared, partial z squared. And in fact, we could solve such problems, even in here. All right, so these are heat equations. The other kind of problem that we study in this chapter is a wave equation, which looks something like this: partial squared u, partial x squared equals to 1 over v squared, partial squared u, partial t squared. This is a so-called wave equation. Because the solutions to this partial differential equation actually model like waves on a string, all right? And here v is actually the speed of the wave. We can derive this from looking at Newton's second law on a little segment of string. If you just look at like a little string segment and study the force of the tension on it, you can derive this with about 10 minutes of like physics 231. I often do that in here. So we'll learn how to solve the wave equation, all right? And then there's a third equation that we like to solve in here, which is simply nabla squared u equals to 0, aka uxx plus uyy equals to 0 typically. This is just Laplace's equation. All right, so we'll learn how to solve that one as well. These are all in chapter 10 of the text. And they're all kind of solved in the same way, give or take. Now, what is Laplace's equation? Well, so for example, in electrostatics, you guys will learn that the electric field, right, is equal to minus the gradient of the voltage function, right? And so if you calculate the divergence of the electric field, the divergence of the electric field is equal to minus the divergence of the gradient, but the divergence of the gradient is exactly the Laplacian of the voltage. On the other hand, if you study electrostatics, eventually you learn that the divergence of the electric field is equal to the charge density divided by epsilon naught. This is equal to the charge density divided by the permittivity of free space. So in the absence of charge, if the charge density is 0, that means that the divergence of the electric field is 0, right? No charge. So in short, the voltage function in an electrostatic situation has to be a solution of Laplace's function, Laplace's equation rather. So this models, among other things, voltage function in electrostatics. All right. So if we can solve Laplace's equation in some region in 2 dimensions subject to some boundary conditions, that corresponds to finding the voltage as a function of position x and y. Here there's no time. All right. This particular the first 2 problems have time in them, right? But this one has no time. It just has 2 independent variables, 1x, 1y, both spatial variables, right? Of course, you could also, same thing for 3 dimensions, right? In the 3-dimensional Laplace equation, we could also try to solve that. Do any of you know where Laplace's equation would come up? Where else it would come up? How about in the previous situation, like up here in the heat equation, if we're looking for a solution to the heat equation, which is a static solution, right? Like if you're looking for solutions to the heat equation which are not changing in time, you would set partial u partial to t equal to 0, right? And then that would be Laplace's equation again, right? Laplace's equation also comes up if you study laminar flow, liquid flow of liquids that's not too turbulent. If you study that, you also find that Laplace's equation appears there. So that's another application. Anyway, these are the 3 equations we're going to learn how to solve. There are many other partial differential equations that are of interest to physics. So this is just a note. I'll squeeze it in here. So like E and M, if you get right down to it, we have these equations. The divergence of the electric field is rho over epsilon naught. The curl of the electric field is minus partial B partial T, right? Oh man, I'm forgetting some dimensional constants in here, I think. Oh, well, I'm not. I may be up to a sign and a, So here you have mu naught J plus epsilon naught partial E partial T, I think it is. And of course the divergence of the magnetic field equal to 0. These are all partial differential equations when you sort through them. They're partial differential equations in time and space as independent variables. And there are 6 dependent variables here particularly the XYZ components of the electric field and the XYZ components of the magnetic field, right? So to understand electromagnetics, which is, physics 232 extended to its more proper generalization, you have to solve this system of 4 partial differential equations given a set of, here rho is the charge density, and this J is the current per unit area time, the so-called current density. So if you're a physics major, you try to learn how to solve these and analyze them, right? Or maybe if you're an electrical engineer, you'll study these in your fields and waves course. But these are the basic equations of electromagnetism, and they're all partial differential equations. That's, you'll spend, if you take a junior level course in electromagnetism, you'll spend most of your time trying to learn how to solve these, right? Quantum mechanics is governed by Schrodinger's equation. If you study Schrodinger's equation, if I was to write it down, what you'd see, again, is a partial differential equation between the wave function and the Hamiltonian. So any kind of basic physics that you study these days, most of them involve some sort of partial differential equation at their base. Fluid flow, the Navier-Stokes equations are, again, partial differential equations. In general relativity, the wave equations that Maxwell found in 1916 or so, again, partial differential equations. My point to you is most of modern physics at its base, at least classically speaking, is partial differential equations. So these are important in terms of trying to solve. And beyond that, goodness gracious, there are so many partial differential equations you come to in industry and science, because what is a partial differential equation? It's an equation involving derivatives where you have more than one independent variable. I don't know about you, but in my life, there's never just one independent variable, right? There's always many different variables acting at once, right? So this context we've been in up to this point of just having one independent variable, that's, very simplistic, right? There's usually more than one. And I'm going to show you the basic techniques to start solving these. All right, but before we actually dive into the solution of these properly, we need to develop a little bit of background on what are called boundary value problems. All right, so let's look at some of those. So this material is in my notes, but not in the textbook. And so what I figured out after teaching this a few semesters was I could vastly streamline the work if I just made like 4 basic propositions that we keep going back to and using. All right. So I'll start with, I'm going to talk about basically 4 different problems. And so this is actually my proposition 8.31 is the solution to this problem. But let me state the problem, and then we'll work through it, okay? So here's the problem. And I want you to appreciate not just the statement of it, but also why it's different than things we've already done, all right? So here is the question. Determine which values of big K bless you. Allow non-trivial solutions to y prime prime plus big K times y equals to 0. Where y prime denotes dy dx, and we have y of 0 equals to y of L equals to 0. So this is the problem. Now, this is going to come up in association with different things, but one thing it'll come up in association with is the heat equation in that possible case that I mentioned. When we have both ends of the rod fixed at 0 temperature, it's going to end up coming up in there, all right? So can you guys tell me what's different about this problem than the ones we've already solved? I mean, two things that kind of stand out at you. I'll point out the one that's kind of obvious. There's a k in it, right? I'm not solving one problem. I'm solving a whole family of problems. That's one thing. What else, though? I'll ask you a leading question. Is this an initial value question? Or why is this not an initial value problem? We know that there always exists a solution to an initial value problem, right? So if this wasn't an initial value problem, the answer would be rather boring. It doesn't matter what k is. There's always a solution. We know. It's the IVP. We solved that thing. What's the deal here, though? Look at this. See that? 0 and L. And we're assuming that L is not equal to 0, okay? That's new. I'm giving you data about the solution that we're seeking at different points of the independent variable. It may or may not be possible to actually find a solution given that kind of data. Let's see why. How do we solve this? Well, k, and I should have emphasized here, k is a real number. If k is a real number, there's a trichotomy, right? What are the cases? How about case 1? K equals to 0. If k equals to 0, what are we solving? Y prime prime equal to 0, right? And you can write down the solution to that. Hopefully before you heard me say anything, right? You should have been able to write, hey, what solution is that? C1x plus C2. We knew that back in Calculus 1, right? Integrate 2 times. There's your solution. But then what? Y of 0 is C2, and Y of L is C1L plus C2. Put those equal to 0. What's my solution? Right, because C2 is 0, and then C1 times L is 0. Divide by L, C1, 0. So apparently, case 1, useless, right? No interesting solutions. So we go on to case 2. What would that be? How about k positive, right? K greater than 0. Now, I propose, for reasons that will become clear very soon, that in the case k is positive, we should write it as the square of some other thing. So let's say k is equal to beta squared for beta positive without loss of generality. Right? And we're trying to solve then y prime prime plus beta squared y equal to 0. What I'm doing right now is not very good storytelling. We'll learn very soon that, you know, you should save the interesting part of the story for the end. I'm actually telling you the interesting part of the story in the middle. It's not the best storytelling, because we're about to find non-trivial solutions here, I think. What are solutions to this? We got what? Lambda squared plus beta squared equal to 0. Therefore, lambda is equal to plus or minus I beta. In other words, y is equal to c1 cosine beta x plus c2 sine beta x, right? And so we plug in the boundary values. What do we get? Y of 0 is c1 cosine of 0 plus c2 sine of 0, right? Y of L is c1 cosine of beta times L plus C2 sine of beta times L. What's that tell us? What's sine of 0? 0, right? What's cosine of 0? It's 1, right? So the first equation being 0 tells us what? It tells us that C1 is equal to 0, right? So the second equation then actually gives us information about C2. It says that C2 times the sine of beta L should be equal to 0. Yes?
Was there significance, so when you chose K to equal to beta squared, was there any significance to making beta greater than 0, even though if beta is positive or negative, K would still be positive?
Yeah, well, by making beta positive, that makes it unambiguous. If I didn't say that, then there could be two different betas, which would lead to the same K. But I just want to remove that ambiguity. It becomes more obvious why I want to do it very soon. So I got C1 is 0. I've got C2 times sine of beta L is 0. Can we let C2 be 0? I mean, we can, but what does that do? If C1 and C2 are both 0, we're back to the trivial solution, which we don't care about, right? So C2 cannot be 0, which forces what? Sine of beta L to be 0. What does that say? Right? That says that beta L is equal to n pi for some n in the natural numbers. And there's where I used beta being positive, because see here, beta L is greater than 0, implies that n must be greater than 0. If I had not done that, then I would have to let n be an integer, possibly negative but not 0. But that's just kind of like capturing the same solution in kind of an awkward way. Like if I use n equals 1 and n equals minus 1, you know, the minus 1 is just the same solution, really. With, if I put a minus in the argument, it's not really a different thing. Like sine of beta x and sine of minus beta x, they're kind of the same. Yeah, so we don't care about that. We want to eliminate it. That's why I made beta positive. Okay, great. Then apparently, beta is equal to n pi over L, right? And then and what does that actually say? What does that make K? That says that K is equal to n squared pi squared over L squared, right? So apparently, no, not just any value of K will do. There's a discrete, well, there's a continuous spectrum. I mean, there's infinitely many choices of K which will do, but they're rather specific choices, aren't they? K has to be n squared pi squared divided by L squared to find a non-trivial solution to this boundary value problem. Now, you're like, wait a second, hold on, flag on the play. You're not done yet. There's another case. There's a third case, which is K less than 0, right? We still need to see, well, let me finish this up, though. What's the solution we found? In summary, we've got y sub n of x equals to, how's it go? Well, any constant, really. So I'll just say sine. I'll just drop the constant to 1. So basically, sine of beta L. What's sine of beta x, rather? Sine of n pi x over L solves the boundary value problem here. Okay? And that's for n equals to what? 1, 2, 3, ... So I've almost answered the problem. We figured out K must be n squared pi squared for L squared. We're not absolutely sure there's no other possibility yet. We need to look at case 3. But in that case, the solution is sine of n pi x over L, right? And you can check that the solution makes sense, right? For each n, this works. What happens to this function when you plug in x equals to 0? You get what? X equal to 0 gives you 0. What happens when you plug in L? the L's cancel, right? And you get sine of n pi, but sine of n pi is 0, all right? So let's look at case 3, which I should have made case 2 for better storytelling, but oh well. Case 3 would be k less than 0, hence k equals to minus beta squared in this case, right? Where beta is positive to, again, keep it simple. And so then we're facing y prime prime minus beta squared y equals to 0, which has solutions of y is equal to c1 cosh x plus c2 sinh, beta x, c2 sinh beta x. That's the smart way to write the solution here. Certainly you can rewrite e to the beta x and e to the minus beta x in terms of cosh and sinh. This is an equivalent way of characterizing the general solution, which serves our purposes here because when you look at y of 0, you get c1, and when you look at y of L, you get c2 sinh of beta L equals to 0, which implies that beta, well, that implies either c2 is equal to 0 or sinh of beta L is equal to 0, but that says that beta L is equal to 0, which implies that beta is equal to 0, which is not possible. Because there's only one 0 for sinh. Sinh of 0 is 0. That's the only time sinh is 0, because the derivative of sinh is cosh, which is always positive. Therefore, sinh is strictly increasing everywhere, which means it doesn't have more than one real 0. The real 0 of sinh at 0 is the only 0 of sinh. So in short, I can take the inverse hyperbolic sine of both sides and just get 0. So what am I saying? In case 3, there is no interesting solution again, in summary. Case 3, boring. So case 2 is where it's at, and that's where the solution of sine n pi x over L is found. So this is one problem that arises. Any questions? Yep.
So by saying that, we're now going forward with whenever we're solving these problems, we always assume k is positive, greater than 0 for all cases.
No, I wouldn't say that. What I would say is that if I'm solving y prime prime plus ky equals to 0 subject to this particular set of boundary conditions, then I can say that the only non-trivial solutions which exist have the form sine n pi x over L, where n is equal to 1, 2, 3, and we need that k is equal to n squared pi squared over L squared. Those are the only non-trivial solutions to this boundary value problem. But whether or not k could be positive or negative, that depends on the boundary values. Like, we can change this problem a little bit, and there'll be a different answer. Let me see here, I'll show you. So actually, let me not work through the details, but very similar details show that if you put prime here and here, then that's my proposition 8.32. And what ends up, in the case that you work that out, almost the same calculation goes through. Cases 1 and 3 are boring. Case 2 is the interesting one. K is still, works out to n squared pi squared over L squared. But just to summarize what happens if you go through what I just went through, but for that case. Similar calculations show k must be equal to n squared pi squared over L squared, and we get solutions y sub n of x equal to cosine of n pi x over L, which is really, if you think about it for a second, not surprising, because if we differentiate cosine of n pi x over L, what happens? You get sine of n pi x over L, right? And then if you plug in 0 and plug in L, it's 0 for essentially the same reasons we just talked about. And by details I haven't shown, again, there's nothing interesting in the cases. Oh, there is one other thing, though. Or what? And what? Actually, case one, let me not pull a fast one on you. Does case one work this time? Check it out, right? K equals to 0 gives what? Y prime prime equal to 0, which tells me that y is equal to c1x plus c2. Can we find choices of c1 and c2 which make the derivative 0 at both endpoints? What's y prime? Y prime of x is what? Is c1, right? So if you set that equal to 0, that gives us y prime of 0 equal to 0, and it also gives us y prime of L equals to 0. Bingo! We've satisfied the boundary values. Woo-hoo. Which means that y sub 0 of x equals to c2 is also a possible. These are called eigensolutions, by the way. Yeah. A possible characteristic solution to this boundary value problem. Now, to get a case where k is negative, I need to look at mixed endpoints, if I remember right. So let's try to work this one out. I could have worked this out, and actually this is more important than what I'm about to work out in terms of problems we'll solve later. Like, we're more often coming to the case of cosine or sine solutions than the one I'm about to do, but it's probably worthwhile for our. So you guys, you tell me which one, we would make one or the other of these be just a function, the other one be a derivative. What do you guys want to do? First one, 0. Okay, so just so y of 0 is 0, but y prime of 0 is not 0. So by the way, the derivative being 0 at the endpoints for the heat equation, that would correspond to the insulation. Like this would be something like we're insulating at L, and we're putting an ice bath at 0. That would be the kind of physical situation which brought you to this sort of mixed boundary value problem. All right. All right, so let's work through it. Case 0, what do we got? K equals to 0, so that gives us y prime prime equal to 0, so y is equal to c1x plus c2, hence y of 0 is what? c2, which is equal to 0, and y prime of 0, y prime of L is c1, which is equal to 0. Done. Nothing, right? Nothing here, right? Nothing here except for the 0 solution. So, yeah. Case 2, according to my current lingo, k positive, right? So we're solving what? We're solving y prime prime plus beta squared y equals to 0. This gives me y is equal to c1 cosine beta x plus c2 sine beta x. You're like, this lecture is all reruns. Like, we've seen these things before, right? Like, everything I'm doing here, is this new? Not really. I mean, these are things you've seen before. Maybe the using Cosh and Cinch is new, but I warned you that it would be useful earlier. This is where it's useful. Anyway, so what's y of 0? Gives me a c1 equal to 0, right? And how about what's y prime of 0? Well, what's y prime? First of all, what's y prime of x? Fine, I'll do it down here. What's y prime of x? Y prime is minus c1 beta sine beta x by the chain rule, right? Plus c2 beta cosine beta x. right? So if I plug in y prime of L, keep in mind that C1's already been shown to be 0 by the last boundary value. So y prime of L is what? It's C2 beta, what we got? Cosine beta L. Actually, I'm starting to wonder, Joseph, if any of the k's work out to be negative in this current story I'm telling. I'm not so sure. See, because I think I can solve that being 0 if I just make the right choice of beta L. So it looks like k positive wins again. Dang it. Man. Where did this... I know k can be negative for certain problems, but now you've got me wondering, where on earth did that happen? Oops, I shouldn't have erased all that. Well, let's finish up case 2 before we get to case 3, which is, case 3 is going to be like boring. There will be no solutions. But anyway, so this one, if beta is positive and C2 we can't let be 0, this forces the cosine of beta L to be 0, right? So this implies that cosine of beta L equals to 0, which means that beta L is equal to pi over 2 plus n, 2n plus 1 for n in the, not integers, but positive count numbers, right? So that would start at, oh, maybe I can do minus 1 since I did that. Yeah, minus 1. So if I put a 2n minus 1 and I'm sampling, excuse me. Oh, people listening. Poor saps. Anyway, yowzers. I guess if I was a better person, I'd go edit that out. It's not happening though. Let's see here. So, yeah. If n equals 1, 2n minus 1 is 1. So this starts out at pi over 2. Then you got 3 pi over 2, 5 pi over 2, 7 pi over 2, so forth. Those are the zeros of cosine. Positive zeros, right? Because beta L is positive, so I'm looking for positive zeros of cosine. So what's that tell us? That tells us that beta is equal to pi over 2L times 2n minus 1, right? And in summary, case 2 suggests what? What's k? K is kind of weird here, right? K is equal to pi squared times 2n minus 1 squared divided by 4L squared. And my solutions are apparently cosine, so let's say yn is equal to cosine of pi times 2n minus 1 divided by 2L times x. So there you go. That's the non-trivial solutions we found in case 2. That's the value k has to be to satisfy this mixed endpoint. Now, to be clear, I'm not done logically until I've made sure there's nothing left lurking for us in case 3, right? So let's just go through that. We're going to find nothing is interesting over here, but, you know, logically we should check on it, which gives us what? This is y is equal to c1 cosh beta x plus c2 sinh beta x. And so let's see here, y of 0 is c1 because cosh of 0 is 0, cosh of 0 is 1, sinh of 0 is 0. What's y prime? Well, y prime of x is what? Beta c2 cosh beta x, yeah? Because c1 is 0, so this piece is gone, so we just have that. And then when you look at y prime of L, which is allegedly 0, that gives us beta c2 cosh of beta L equal to 0. Hyperbolic cosine is never 0. L is assumed to be non-zero. This forces beta to be 0, but that's not allowed. So in short, we can't solve the boundary values we can't fit the boundary values in case 3. So case 2 had everything interesting. We already boxed it in red right there. By the way, this is the result of section 8.33 in my notes on page 203. We have just derived proposition 8.33, which says the same as what I just said. All right? And then, yeah, funny enough, so if you do the same problem, but instead do the derivative being if you put the derivative 0 at 0 and you make y of L being 0, so if you just move the prime to the other, it's more or less the same. That's my proposition 8.34. Again, k is positive. So, man, I don't know. We're going to find a problem eventually where k works out to be negative. It happens. But it hasn't happened for us yet, that's for sure. Huh. Man, that's a good question. I don't know how to answer it at the moment. That's aggravating me. All right, let's go on. So I'm going to refer to these problems in our future work. The point of me doing this right now is as you solve homework problems, right, going forward, using the method I'm about to show you, when you get to a boundary value problem, which is one of these 4 standard types, you may refer to the propositions 8.31, 8.32, 8.33, 8.34, which, if you'd like to be more brief, you can say by boundary value, by BVP1, BVP2, BVP3, BVP4, like this. Well, anyway, let's just to be safe, proposition 8. Either 3.1, 3.2, 3.33. Look at the notes, use the proposition number, just refer to that and say by that proposition, we know the solution is that. All right? And you don't have to go through all of this again whenever you come to such a problem. Right? Because what I've realized working through it for myself is if you rederive this stuff in the context of the problems going forward, it's about half of the length of the solution, and it's not really interesting. So I think it's better for us to kind of make this a black box of sorts that we can refer to and just use it, right? Like an op-amp or some kind of modular design, right? I mean, that's what theorems are in mathematics, right? Okay. So now that we have this, let's try to solve a problem. So we'll start by working on the heat equation. Let's see here. Give me just a second to locate the statement of the problem. Make sure I start us out in the right way. Aw, come on. Well, that is frustrating. It's got links to everything except for the one I want. Not cool. That's not good. Sorry, I'm trying to, like I said, I'm trying to find the, have to go back. You know, I wrote solutions at some point in the past. But you know how many times I've taught this course? A lot. So finding which year... I found it. Whew, goodness gracious. All right. This is going to be kind of anticlimactic, but here it is. Partial u, partial... Let's try to solve. Partial u, partial t equal to 3 partial squared u partial x squared. All right. On 0 less than x, 0 less than x less than pi. All right. We're solving on that. Subject to insulated boundary point, so subject to boundary condition, partial u, partial x, 0 comma t equal to partial u, partial x, L comma t equal to 0 for t greater than 0. So that says that we're insulating the endpoints of the rod. Oh, and my L is what? Pi, right? So I should put pi here. And where, here's the initial condition, u of x comma 0 is equal to x. That's not right. That doesn't even make sense. What? How can you have that be x? Sorry, I don't like that. Just give me a second here. Yeah, there it is. That's problem number 3 in section 10.5. So maybe there's something I don't understand. All right, something wrong with my intuition. Fine, let's go on. What I'm worrying about won't really change the larger story I'm telling you. So if I'm right and it shouldn't be that, it will not ruin any of our work going forward. So don't, not a big deal. All right. And besides, I haven't even told you what bothers me about it, so maybe you don't know. All right. And we'd like to solve this heat equation. So let me go through the steps. So what we do is we suppose that u of x comma t can be written as a product of functions of x and t. So x of x and t of t. All right? So if we do that, then when you calculate things like partial u, partial t, right? If we take a time derivative of x, t, what's that going to do? Well, x is just a function of x, right? So big X pulls out. All right? So if we have partial u, partial t, we're going to use the notation that that's really just xt prime. And we'll understand that when we write t prime, we're really just talking about an ordinary derivative with respect to time on the time part of this product solution. And the same thing is true if we calculate partial derivatives with respect to x. So I can pull the t out to the side, right? And so that would be x prime t. And of course, we can also calculate second derivatives. And by a similar logic, that would be x prime prime t. So now you might wonder, why on earth would you suppose a solution can be written as a product of solutions of one variable, right? And that's a reasonable question. And there are various answers that can be given to that. For the wave equation, there's an easier answer to give for the wave equation. For wave equations, we can look at waves on a string, right? And one of the possibilities is like a standing wave, right? But you can actually see sort of, if you look at waves on a string, you can see like there's some kind of particular shape of the wave, right? And then it's moving with time. So if you can somehow, and if you study trigonometry, you can see that you can write it as a product of a space solution and a time solution. If I do like products of sines and cosines can be rewritten anyway. I'm not sure I'm being convincing, but if you study the wave equation, you can kind of come to a physical reasoning that this a product of functions of space and time because of, just think about waves on a string. Now here I don't think that's at all obvious, but so here I probably should give you the less satisfying explanation that it works. Although it's not clear that it works at the moment. So what does this get for us? What happens when we plug in the product solution into the differential equation? Right. By the way, this is called separation of variables, what we're currently doing. Not to be confused with the earlier separation of variables, but if you confuse this with the earlier separation of variables, you are really, really lost. Because this is nothing like it, except that we're going to put functions of x on one side and functions of t on the other. That's the sense in which it's separation. All right, so what we got? We have partial u partial t is xt prime. And we've got equals to 3 x prime prime t. Assuming that we're not looking at the zero solution, we can divide by the solution. Right? So this implies that t prime over, let's say, 3t is equal to x prime prime over x. I'll put the 3 with the t because it makes my life easier. Any questions? So look at what we're looking at here. We've got, on the left-hand side, this is a function of t. Over here, we're looking at a function of x, right? In other words, if you could take this differential equation and you could differentiate it with respect to x, right? And that would show you get a constant with respect to x. You could differentiate it with respect to t. You could see you get a constant with respect to t, right? If you've got a constant with respect to x and a constant with respect to t, what are you looking at? What's that? What kind of functions are constants with respect to both the x and t variable, x and t being independent? What's that? Multivariable? How about like 3? You give me x and t, I give you back the number 3. Is this a constant with respect to x and t? Or maybe I just spit back the number 5, 42, pi, whatever. Pick a number, any number. A constant, a genuinely constant function is a constant with respect to any choice of variable. So the only common constant functions to both x and t are just constants, right? In other words, there exists a k, or I'll say minus k, for reasons that will become obvious here in a second. So I can set that equals to minus k, right? So apparently, I face, what do I face? I must face x prime prime over x equals to minus k, aka x prime prime plus kx equals to 0. The reason I put the minus there is so it matches up with our work from just before I wrote this, okay? Because I want to use that modular design that I set forth, yeah? So I gotta, and how about the time? Time, we've got t prime equals to minus, looks like minus 3kt. Oh, hey, that we can solve. That says lambda is equal to minus 3k. So thus, t of t is just equal to the exponential of minus 3kt, right? Yay. Maybe I should put a t sub k on that because it depends on k, right? Whatever, but the time equation we can solve. Not a big deal. Now, what about the spatial equation? So what have so far have I used what? I have used the pink underline, the actual PDE. Next up, I'm going to use the boundary conditions, right? So what would the boundary conditions say? So we've got, you know, ux at 0t, which would, by the way, be x prime of 0 times t of t equal to 0. And ux at pi comma t would be, by the way, x prime of pi times t of t equals to 0, right? But those hold for all t, right? So you see, the boundary conditions given for the temperature function, in fact, imply corresponding boundary conditions. Curses. Yeah, you guys used to laugh at my suffering. It's understandable. All right. I could just be smarter and not tape these. Let's see here. Oh, okay, so x prime, so thus, what I'm getting to here is x prime of 0 is equal to 0, and x prime of pi is equal to 0. Hey, this brings us back to problem 2, which is very much like problem 1 that I worked out. The answer was, thus, therefore, k is equal to n squared, pi squared, divided by L squared, which is, by the way, equal to n squared pi squared over pi squared, also known as n squared, since L is equal to pi here, right? And we have solutions x sub n of x equals to cosine of n pi x over L, which, of course, is equal to cosine of just nx. By the way, if I give you a boundary value problem with L equal to pi, you should remember that as you write course evaluations, because I was being nice. Because if you make L equal to pi, the pi's cancel. So less pi for everyone, right? Which doesn't sound good, but it's actually a good thing, because we don't like to write pi 1,000 times. Anyway, xn of x, there you go. And in retrospect, we have then that Tn, the corresponding Tn of t would be what? Exponential